Hello, number theory fans. I gave you some exercises to work on for Diophantine equations, and the first few probably came off without a hitch, but when we tried some of the applications, maybe we hit a roadblock. And there's one thing in the applications that I had not addressed in my lectures, and I'm going to address it now through the use of an example. This is going to be a Diophantine equation, or it's going to yield a Diophantine equation. Find all combinations of 14-cent stamps and 9-cent stamps that can be used to pay 23-cent postage. So here's what we do. We let x equal the number of 14-cent stamps. We'll let y equal the number of 9-cent stamps. And so what we want x and y such that 14 cents times x plus 9 cents times y is equal to 23 cents. And we can't have half of a postage stamp. We can't have half of a 14-cent stamp or 7/8 of a 9-cent postage stamp. X and Y have to be whole numbers. And we're looking for all combinations of 14-cent stamps and 9-cent stamps that will give us 23 cents postage. So we have to solve this Diophantine equation. And let me illustrate this. We have AX plus BY equals C. So I guess the first thing that we have to do is check to see if D divides C, where D is the greatest common divisor of A and B. Well, 14 is 2 times 7, and 9 is 3 times 3. These two things have no factors in common. D equals 1. So D definitely divides C. Or I'll say 1 definitely divides 23. And underneath I'll say the significance of this is that D divides C. So solutions exist to that equation. Next step, find a particular solution to AX plus BY equals D. 14x plus 9y equals 1. And again, the significance of D here is that this is the greatest common divisor of A and B. To solve this equation, we use the Euclidean algorithm to find the greatest common divisor of A and B. So we set it up this way. A equals quotient times divisor plus remainder. And that is 14 equals 1 times 9 plus remainder of 5. Okay. Now, remember what we do. The old divisor now becomes the dividend, and the old remainder now becomes the divisor. So let's see, 9 is equal to 1 times 5 plus remainder of 4. Whoops, whoops, whoops. And the old divisor becomes the new dividend, and the old remainder becomes the new divisor. And 5 is equal to 1 times 4 plus a remainder of 1. So now again, now again, the old divisor becomes the new dividend. And the old remainder becomes the new divisor. And here's what we have. 4 equals 1 times 1. No, it doesn't. 4 equals 4 times 1 plus a remainder of 0. The last non-zero remainder is the greatest common divisor of 14 and 9. And we'll call this equation equation 1. Then working backwards, we'll label its predecessor equation 2, and we'll label its predecessor equation 3. So express the last non-zero remainder in terms of its two immediate predecessors. Let's see. What what precedes 1 is a remainder? 4. And what preceded 4 is a remainder? 5. Okay. So from equation 1, we get 1 equals 5 minus 4. And we express the smaller of the two, 4 and 5, in terms of its two immediate predecessors. Using equation 2. So by equation 2, 4 equals 9 minus 5. And we simplify things a little bit. And we get 5 minus a negative 5 is 2 times 5 minus 9. Okay. And now we express the smaller of these two, 5 and 9. And the smaller of these is 5. We express 5 in terms of its two immediate predecessors. And let's see, as a divisor, well, let's see. We have 5 expressed in terms of 9 and 14 via equation 3. Oh, hold on a minute. Let me write this equation over here. Okay. And again, we take the smaller of these two, which is 5, and express it in terms of its two immediate predecessors, 9 and 14. So let's see, we have 1 equals 2 times 5 minus 9. So that's 1 equals 2 times 5. And 9, let's see, by equation, no, I'm being an idiot, excuse me. The smaller of the two, 5 and 9. So I've got to take 5, and using equation 3, I have 5 equals 14 minus 9. And I'll simplify that. 1 equals 2 times 14. And 2 times negative 9 minus another negative 9 is minus 3 times negative 9. Oh, I'm sorry. Minus 3 times 9. Now we rewrite it in the exact form ax plus by equals d. So a is 14. We have 14 times 2 plus 9, which is b, times -3 equals 1. Now, does this work, first of all? 28 minus 27 is 1. Okay, good, it works. This is our x naught, y naught. Solution to ax plus by equals d. Okay, good. 3. We want to get it in this form, let's see. A is 14, so ax star plus b, but b is 9, y star equals, and what did we want? 23, was that right? 23, I think it was. Okay, this is the form that we wanted in. And x star, y star will be our particular solution to the equation ax plus by equals c, or ax plus by equals 23. Well, what do I have to multiply this equation by to make the right-hand side equal to 23? Got to multiply it by 23, right? So I have 23 times 14 times 2 plus 9 times -3 equals 23 times 1. And now I'm going to distribute the 23 on the left-hand side, but I'm going to do it in such a way that I preserve the identity of A and B. So I'll get 23 times, no, I won't either. I'll get 14 times 23 times 2 is 46, plus 9 times 23 times -3, -69, equals 23. So there we have it. A x star plus b y star equals c. That's exactly the form that we wanted. And we have our particular solution. To ax plus by equals c. Okay. -46, -23. No, -69. Now we find the general solution. And to do that, we have to find the complementary solution. And we found out that this is b over dt minus a over dt for all integers t. Well, let's see. D is the greatest common divisor of A and B, but D was 1, wasn't it? So we have BT minus AT for all integers T. And B is 9. And A is 14. This is our complementary solution. What to do now? Okay. We just add the two solutions together. And we can add these two things component-wise. So we get 46 plus 9t and negative 69 minus 14t for any value of t, for any integer value of t. This will give us a solution to the original equation, 14x plus 19y equals 23. Now, there is a catch. The values of t that we choose in order to work for this application have to yield non-negative values for X, the number of 14-cent stamps, and Y, the number of 9-cent stamps, because we can't have negative 11 14-cent stamps, but we can't have negative 36 9-cent stamps. Now, it is possible to have 0 14-cent stamps or 0 9-cent stamps. That's possible. But we can't have a negative number for X, the value of 14-cent stamps, or Y, the value of 9-cent stamps. X and Y both have to be greater than 0. So it turns out that for our application, only those values of t that yield non-zero values both for X and for Y are going to be valid. So X and Y have to be greater than or equal to 0. So what does this tell us? Here's X, here's Y. So X, 46 plus 9t, has to be greater than or equal to 0. And Y, which equals negative 69 minus 14t, they both have to be greater than or equal to 0. So we'll see what values of t make this happen. I will subtract 46 from both sides. And I get 9t greater than or equal to negative 46. And I get t greater than or equal to negative 46 over 9. Which equals negative 45 minus 1 over 9. And that is negative 45 over 9 minus 1/9, which equals negative 5 minus 1/9. T is greater than or equal to negative 5 minus 1/9. So let's see, negative 5 minus 1/9 is less than negative 5. So what this means as far as yielding integer values is that t has to be greater than or equal to negative 5. But this is just the restriction on X. What about the restriction on Y? Okay. Looking at this, we have negative 14t is greater than or equal to, I add 69 to both sides, okay? And then I divide both sides by negative 14. 69 over negative 14. And you know what? I just divided both sides by a negative number, so what has to happen to this inequality? We have to reverse it, don't we? So t is now less than negative 69 over 14. And what is that equal to in terms of multiples of 14? It's negative 56 plus 13 over 14. So negative 56 over 14 minus 13 over 14. See, this is negative 4, isn't it? So t is less than or equal to negative 4 minus 13/14. Can t be equal to negative 4? If t is negative 4, it won't be less than 4 minus 13/14. So no, t can't be equal to negative 4. So the negative number that is immediately less than 4 minus negative 13/14 is negative 5. Okay, this is the restriction on y. Holy moly. Both have to be true. T has to be greater than or equal to negative 5 and less than or equal to negative 5. Can you believe this? T equals negative 5 yields the only solution. Son of a gun. What was my solution again? Let's see, 46 plus 9t. And what, negative 69 minus 14t. Is that what it was? Let's see. Yeah. T equals negative 5. 46 plus 9 times negative 5. And negative 69 minus 14 times negative 5. Let's see, 46 minus 45 is 1. Let's see, negative 5 times negative 14, that's positive 70 minus 69 is, oh my goodness. X equal 1, y equal 1 is the only solution. Well, let's check. Let's see, 14 times x plus 9 times y equals 23. And yes, that is the only solution. I will be a son of a gun. Well, everybody, I hope that helps with the application problems involving Diophantine equations. Get to work on these now that we've seen how we solve these things for applications. I'll have another video or two coming out, what's today, Thursday? Have another video or two coming out hopefully before the end of the weekend. And again, stay safe, exercise sound judgment in everything that you do. And I am really looking forward to seeing all of you face to face.